Hello! We are going to continue our discussion of irrotational flow, and before we get started, yes, I'm wearing a tie. I do own a tie, so I thought I would look a little nicer for today's lecture. Anyway, irrotational flow, streamlines, streak lines, and path lines. That's the objective of today's lecture, and we're going to talk about the mathematical derivation of a streamline specifically. So, we're going to distinguish first between what a streamline, a streak line, and a path line are, and we're going to include timeline in that. We're going to develop a couple of mathematical relationships associated with that, and then I'm going to do an example. Let's get started. So a streamline is by definition a line that's everywhere tangent to the local velocity vector field, to the vector. So here's an airfoil right here, and you've got this velocity vector field there that I've drawn, and so a streamline then naturally would pass right through each one such that it's tangent to the local velocity vector field. And we use the variable psi to describe the streamline. A path line is a path that's traversed, is the path traversed by a given particle. So I just put a little particle on there and I had it follow along the streamline. So if we started that particle on the streamline, it would stay on the streamline. The streak line is the locus of particles which have earlier passed through a prescribed point in space. Well, isn't that exactly what the path line was? It sounds like it. We prescribed, if I prescribed this point in space, or if I took this point and ran it backwards, right, it would say it's the locus of particles which have earlier passed through a prescribed point in space. So of course it would follow the path line, streak line, streamline. The timeline is a set of fluid particles that form a line at any given instant. So if I had a streak camera or an instant camera, it would appear to be that line of points along the streamline. So it seems like those are all the same definition, and they are for steady flow. But keep these in mind, and I'll show you a little video in a minute that really highlights the differences in unsteady flow. So they're all the same steady flow, and streak lines are what we visualize in a wind tunnel. So normally, if somebody is making a streak line, it's a locus of particles which have earlier passed through a prescribed point in space. You have a wand, and out of that wand is shooting smoke. That is the point at which all the smoke, irrespective of where it ends up, initially started. So you could trace it all back to that single point. So keep that in mind, that really technically what you see in a wind tunnel is a streak line. All right, this is a video, and you guys know I love these National Committee of Fluid Dynamic videos. This one comes out of the flow visualization video, and I recommend you watch the whole thing on your own. But I'll show you just this little part here that highlights the differences between a streamline, streak line, and path line.
Here is a single marked element entering at a fixed time in the cycle of a plate. As before, we superpose its path line. Now compare the path line with a succession of instantaneous streak lines entering through the same point. None of the instantaneous streak lines coincides with the path line. Here is a second element entering through the same point, but starting at a different time in the cycle of the plate. Notice that its path line crosses that of the first element almost at right angles, and it leaves around the other side of the plate. Now you see elements marked at both times in the cycle of the plate. If we superpose the path line of the second element, and compare it with a set of streak lines through the same point, you can see that none of them coincide with a second path line either. Now let's see about the streamlines. In order to find the streamlines, we need the direction of the velocity at each point. We can find this from combined time streak markers, such as you see here. If we take a transparency of one frame of the multiple time streak lines and overlay on it another transparency taken a few moments later, we can connect the endpoints of the streak lines and show the particle paths for short time intervals. Here you see the short dashes made by connecting the endpoints of the time streak lines. They show us the velocity direction at each point. If we draw lines parallel to them, these are the streamlines. The total streamline picture you see here is for the same instant that the first particle we observed with a path line entered the frame. The dotted streamline is the one that passes through the same point. If we compare the dotted streamline with the path line through the same point and at the same instant in time, you see they are quite different. If we compare the dotted streamline with a set of streak lines entering through the same point, they do not coincide either. In a transient flow, the streak line, the path line, and the streamline are all different. If the streak lines move sidewise, as you see here, then the flow is transient, and we cannot use the streak lines for streamlines. In a transient flow, we must work out the velocity field from some kind of combined time streak markers.
Okay, so there are several ways we can define a streamline. We'll go at this in a couple of mathematical ways. The first one is to recognize that the streamline is the line everywhere tangent to the local velocity vector field. So I can draw a tangent velocity there, and I can recognize that that velocity vector is made up of scalar components. So there is a u velocity component, a v velocity, and a w. And those are scalars. The u, v, w are scalar, and they're made a vector by including the unit normals in their direction, right? So together, those three scalars make up a vector. And those three scalars can be functions of x, y, z, and t, each one of them. There's also a position vector that we could define as a unit vector, right, dr, and it has positions of dx and I, dy and j, and dz and k. So it's just like the velocity vector. So I can take the ratio of those two. I can just take the ratio. It's a mathematical formulation. And it's just a simple geometric formulation related to the similar triangle rule, right? So the ratio of similar triangles. So here I have the ratio of the vector r to v, and it forms these other ratios. Dx goes to u, like dy would go to v, and dz would go to w. So in 2D, if I get rid of or ignore this, I have this equation here, and I can then move everything to the left-hand side and form this, this relationship between the velocity in the u direction times dy minus the velocity in the v direction times dx. Let's put that on hold for a moment, and we'll come back to that a bit later, but just keep these relationships in mind, that they are true for the relationship between the velocity and a unit normal tangent to a vector, a tangent to the streamline. Okay, the second definition I tend to like better because it's a bit more solid. Think about the continuity equation. The streamline is an exact solution to the continuity equation. So here I'm showing the continuity equation, partial rho partial t plus the dot product del dot rho v, or the curl of v. Now, if I were to assume that the flow is incompressible, that means rho is equal to a constant, right? Then this term drops out. Partial rho, partial t. Of course, anything that's a constant with respect to another variable is going to be 0. In addition, since rho is a constant, I can pull it out of this operator, right? So if I pull it out of the operator, and then I make the recognition that rho can't be 0, I would have this term, right, times rho, and it means then that the onus is on del dot v to be 0. So del dot v is equal to 0 comes from a continuity equation, and it's a very common expression in fluid mechanics. It basically represents the conservation of mass equations in differential form for incompressible flow. So we have, I'm going to expand this out. I'm going to go ahead and take the dot product. So the vectors are gone, and we're just left with the gradients of the scalars must sum to 0. If I make the further requirement that it's 2D, then I can define a streamline as being some analytic function psi is defined to be the u velocity when you take the gradient with respect to y, and it's defined to be the minus v velocity when you take the gradient with respect to x. And so if we just require that, then what happens is if I substitute in, if I take the definition of the stream function and I put it into the continuity equation, I get an exact solution for the continuity equation. So this psi, defined in this way, exactly satisfies two-dimensional incompressible flow. Right? So I take this u and I put it in, so I have partial x operating on u minus partial y operating on v. And you can see due to the cross differentiation rule that this becomes the partial squared of psi partial x partial y minus the partial squared of psi partial x partial y. So that exactly is equal to 0. Therefore, it's an exact solution to the continuity equation. That's kind of clever, I think. So I like that definition of psi. All right, let's think about some concepts of what it means to be a stream function, what it means to be everywhere, that it's tangent to the local velocity field. Is the stream function valid in 3 dimensions? So here is our incompressible version of the stream function. The answer is no. And this is really kind of, I would leave it up to you to give it a try. It would actually be a great coffee time break to try this yourself. But I think that you'll find it to be quite difficult. The trick is can you write a single function that is in some way such that the gradients of it with respect to x, y, and z sum to 0. Is the stream function valid for 2D compressible flow, 2D compressible steady flow? So previously we did incompressible. What about compressibility here? Well, I'm throwing on another requirement. I'm switching compressibility for steady. So in order to get rid of this gradient, right, I'm going to require that the continuity equation be steady, and I'm still requiring that it's 2D, so I'm going to get rid of that. So, whoops, I'm going to get rid of the partial v, partial z term. So really, the answer is yeah, I can do this. I can require that partial psi, partial y is equal to the multiplication of rho times u, and likewise partial psi, partial x is minus rho v. And if I put that into the two-dimensional equation, this guy right here, then of course I still get an exact solution. So it's okay for compressible steady flow and incompressible 2D flow. So compressible steady means, right, you've got a density gradient, but it's just sitting there. It'd be like flow through a steady nozzle, compressible flow through a steady nozzle. All right, can streamlines cross? Don't cross the streams. No, they can't. So that's the basic answer. And why can't they cross? Well, because we specified that the velocity has to be tangent everywhere along the streamline. If they cross at that location, I would have two separate velocities specified for the same point in space. And that violates some sort of law. I'm not sure what. But you can't have that. So really it means then the streamline, there can be no flow normal to the streamline. So if there's no flow normal to the streamline, mass can't cross the streamline, right? It has to have a component of velocity normal to it to cross the streamline. So the streamline then acts like a solid body. So you can imagine that everywhere along the streamline I have a velocity, and so I don't have to require that it satisfy no slip, but it could serve as a solid body within an irrotational flow field. So it's not going to satisfy the no slip boundary condition, but it still could be an irrotational solid body surface. So consider something like this streamline here. And normally we would have, this airfoil, we would have a series of streamlines that would go over the airfoil, and that would be a totally legitimate sort of solution. But we could also think of, what if I wanted this streamline here to be the solid surface? So what if I wanted to investigate flow over a bump? Well, I could do that. This would be the bump, and then you'd have the additional streamlines out here, and there's no problem there. So that particular flow field, whether it's flow over an airfoil, could serve as flow fields over various streamlines and things. Now, let's think about for a second what it means, the value of the streamline itself. What does that mean? So let's consider two streamlines, psi1 and psi2, and they look something like this in space in some xy coordinate system. Now let's specify a control surface that can have an angle relative to the coordinate system. This is a little small dx, so it's a differential flux surface area. And there's its unit normal that defines the orientation of dA in space. And there's just some velocity vector between them. The vector could be something like this here shown. So now, recall that mass flux is equal to m dot equals the integral of rho v dot and dA. So we went over this in the review a bit. And let's apply it to this to the flow between these two streamlines. So we know now that these streamlines can represent a solid surface, and so this is kind of like a nozzle, right? So let's solve for the mass flow rate between the streamlines or the flow through the nozzle. So here's my equation. I'm going to integrate over this control surface, so over this arc length S, into the page Z. And so this is my differential area. dA is ds dz. And my unit normal I've defined here as n hat. But in the coordinate system of x and y, this is really some component in the dx direction, in the x direction as dy, and then some component dxj. So if I insert that in to my definition of the mass flux, then I can simplify my integral quite a bit, and we can go ahead and integrate in the z direction to give us this w, right? Now remember, m dot is what? It's rho v average a. That's by definition what m dot is. So I have a rho here, and this is incompressible, so I'm going to go ahead and get rid of this rho and this rho. And so we're left with the volumetric flow rate, velocity average times area. And if I take the derivative, basically, of this line, I would get this little integral dq, or the differential, dq. V, here's the integrand of the integral, v dot n hat ds. That helped get rid of the integral, but now I have this little differential form. Now the velocity here, we know what that is in terms of the stream function. We know that the velocity is defined as the gradient. This is u, this is v. So it's u times I plus v times j, which in terms of the stream function is what you see here. And then the vector n I defined here, that's the unit normal associated with the flux surface. So I get this little dot product, which I can carry out the dot product. And then I recognize that this inner term here is by definition the total derivative of psi, right? This guy right here, this is by definition the total derivative of psi. So that's from your calculus days. And this w per unit width into the board. So what I've really got is an expression that says dq equals w d psi, which integrates to q divided by w equals the change in psi. So that means that the difference in the value of the stream function represents the volumetric flow rate through that stream function per unit width into the board. That is pretty powerful stuff. So the stream function defines the volumetric flow rate, or the difference in stream functions defines the volumetric flow rate. So in this case, the flow between those two streamlines, where the value is 1 to 7, it would be 6, right? So we've got 6 units of flow. Let's consider what the units are in a minute here. Let's make one more observation, and that is that the value of the streamline, because we picked a coordinate system, isn't arbitrary. When we integrated this equation, this guy here, it's got 2 minus psi 1. So that means that for a flow field where psi is increasing for increasing y, the flow is in the positive direction. If psi 2 is greater than psi 1, then of course this will be a positive quantity. The velocity is moving in the positive direction, right? The flow rate's moving in the positive direction. In a situation where psi 1 is greater than psi 2, it just changes the sign, right? So if psi 1 is greater than psi 2, the flow would be negative, so it's moving from right to left. What are the units of the stream function? Well, now that we know what the stream function represents, or the difference in stream function, the units would be related to the velocity. So you could say, well, psi partial y would be equal to u, so psi has to be then equal to meters squared per second, which also goes along with the idea that it's volumetric flow rate per unit depth. So that's also area per second. All right, so I thought we would do an example now to kind of highlight some of the things that we learned in this lecture. So consider a flow field given by the velocity vector x times a in the I direction and minus x times y in the j direction, and a is 0.3 reciprocal seconds. So what if I asked you to find if the flow is compressible or incompressible, and determine the value of the stream function, and then plot it and tell me what you think the flow field is? So is the flow compressible? This is easy enough to do. We know that for the flow to be compressible, to be incompressible, then it has to satisfy del dot v. We showed that earlier. So we have the velocity here. We can carry out this gradient. We just operate on this. The del operator by definition is this guy right here. And there's our velocity vector. Easy peasy. You just take the derivative, and you'll see that we get a minus a, which is equal to 0, which satisfies this requirement, so it is incompressible. All right, determine the stream function. Well, by definition, we know this to be the case. And I can compare then the velocity, the scalar velocity is this part right here. It's the part preceding the unit normal I, the unit direction I, and then the v velocity component, the scalar component in the v direction is this part right here. So because of the sign, that becomes just ay. So I can easily integrate this. I've got a little differential equation. Now I'm considering this term and this term. and I can integrate this in order to form the top equation. Gives me psi equals axy plus some constant c1, constant of integration, and then likewise I get down here that psi is equal to ax plus c2, some other constant of integration. So by comparing these two, I can see that the constant has to be the same. C1 has to be equal to C2 for those two expressions to be the same. Now, we'll talk more about what that constant means, but I'll tell you now that it's arbitrary, all right? And we'll use it to some great extent later when we build more complex flow fields. So right now, let's just let it be arbitrarily 0. So the stream function, I could write it simply as just psi is equal to x times y. All right, let's plot the stream function. I'm going to do this in MATLAB, and no, that's Maple. I'm going to do this in Maple, and this is what the function looks like. And so what does this look like to you? Well, I think it would be maybe like flow coming in here, and then if the flow is confined between streamlines, I'm imagining that it would go out like that, and then flow comes in here, and it's kind of shoots off in that direction. So it's kind of like a jet hitting a plate, right? That would be one way to think about it, where I have a stagnation streamline coming down and hitting right there in the center. Or I could ignore this plane here and just consider the first quadrant, and it's really flow around a corner, right? This is the MATLAB code that I used to generate this plot, and I have a lecture that I'll upload that goes more into detail about how I did it, but it's fairly simple and straightforward. I keep saying MATLAB. It's Maple, okay, which is just like Mathematica. So have a look at that. We have a site license for this, so you can get this, I think, from IT. All right, so we wanted to introduce what the streamline is. We went through the differences between a streamline, streakline, pathline. We went over some of the characteristics of a streamline, and we derived the functions for it and went over an example. Next time I'll go over rotation and vorticity and get ready for irrotational flow. All right, that was fun. We'll see you again soon.